CC when it was offered. She's like, we have to pick a new plan, you do it. Because she knows I can run the numbers, I can figure out what the best optimal plan on average over a long period of time should be for us. When it comes to little basic things like doing taxes, I'm useless. I'm completely useless because it's not really math. I don't understand accounting. Accounting seems like some kind of hand waving.
It's a little.
We're going to recharacterize your earnings and put them into an offshore equity blah blah blah. What the f talking about? It's division. Why do you got to rename it? Right? So when it comes to this kind of stuff, though, this is when she's like, oh yeah. I mean, funny story, I met her in college when she was taking a stat class and needed help with her homework. That's how it all started. So she does defer to me for like 20 plus years of... 20... No, that's what I found out later. I found it out later, but that's... I mean, she defers to me with anything like this. As soon as it becomes, I wonder, it's like, let's let Sean do it. And if it's like, I'm going to pay taxes, I'm like, babe, here you go. Here's all my money. Just go do your thing that you do. Cool? Let's model this now. Now, what's cool about what we're about to do is, we're about to see not only the distribution that governs Max and his crocs, we're also about to see what would happen if we picked up 10 chicks from Lava Ridge after they hatched them. It's the same exact distribution, because it's 50-50. If they're independent, it's also the same distribution that you would get if you flip the coin 10 times. No. Yes. It's also the same distribution you would get if you dealt a card to yourself and made a note of whether it was red or black. What? Yes, it's all of this, if you do it 10 times, it's binomial, because each draw, each chick, each flip, they're all independent of each other. And if you fix it at 10, they're all going to look, the graphs are all going to look like this. Pretty badass, huh? Okay, here we go. Let's fire it up. Not this.
But for cards, you'd have to put the card back.
Well, yes, that's independent. I kind of making that assumption we'll call it independent. Thank you, Randall. Cool. So dist fill number 3.
So yeah. Program.
Program. Yes, ma'am. Program. I don't know how to put it in stat, so I put it in program instead. Now you have to know what X is modeling. What is X going to model in this case? We're going to take a stop right now and understand this. What is X modeling right now?
The triangle.
Say that again. The number of times he gets them successfully on the right feet. Good, Aaron. The number of times he's trying to put his shoes on is 10. We're going to watch him 10 times, assuming he puts his shoes on 10 times, which he did. What we're interested in making note of is how many times do they make it on the correct feet. Yes? So X is number of times he gets his shoes correct. Correct defined, of course, as left foot, left shoe, right shoe. Some could argue, since he only has one pair of yellow Crocs, if he gets the first shoe on the correct foot, the other one's by default going to be on the correct foot, yes? So really, it's just a matter, does he get the first shoe on the right foot? The next one happens as a consequence. Is that fair enough? So, but still 50-50. Say it again.
What if we threw in 2 different colors?
You only have one pair, though. That's why. We're controlling the experiment to one pair. Fair enough? Okay, good. So now, what's the least number of times he could?
0.
He might not. 0. What's the largest number of times he could? 10. Press enter. At this point, your TI has filled L1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good to go. Fair enough? Okay. Let's make it binomial. And then it asks for the chance. This is why we have to know that 0.5, that 1/2. We had to know that up front, because we're assuming he's guessing. That's the only hypothesis we can test. I'll come back to that momentarily. You might be saying, wait a minute, why are you testing the fact that he's guessing? It looks like he might not be guessing. Hold on, we'll come back. If you don't, it's okay, we'll come back to that. 0.5, it's now done, which means if you go look at stat edit, you will see the distribution of probabilities. And this is fine. Although I realized as this gets more interesting, you guys might like a slight more visual look. So what I did was, if you go back to program, there's another one called dist draw, right above dist fill. Go ahead and select that and press enter twice. It'll give you the graph of your distribution as well. There's your distribution of Max and his Crocs. So here's the number. I'm going to slide this up a little bit. The only thing that sucks is it doesn't label anything. So here, this is number of times he gets his Crocs on the correct feet. the least number of times is 0. The max, woo, we'll get that later. The max number of times is 10. 0 through 10, count it, 0 through 10. 5's in the middle. Is there any coincidence that 5 is up here?
No.
Why is there no coincidence that 5 is up there?
Because that's the most times it's going to show up.
Why?
50% chance.
Because if he averages, yes, row 4 has population. Because if he is truly guessing and he does this 10 times, he should get half of the trials correct. Hopefully that makes sense. So, and you guys have already figured this out. You guys have already figured this out. In a binomial, I'm going to go here. You guys already figured out this little rule here. In a binomial, and this works for any binomial, FYI. One of the neatest things about specific probability distributions is the shortcuts that you get for free. And this is the most important discrete distribution that exists, in my opinion. It's just my opinion, for what it's worth. It's the one that gets used the most. If you ever need to pull the average off of a binomial, you wouldn't even need to make this graph to figure out where the average is. Because the average, which we can call mu, because we have the entire population now in front of us, we can call it mu with confidence. All you've got to do is take how many trials you ran and multiply it by the probability of success on one trial.
No problem.
You guys figured this out last week. You've since forgotten it, and that's okay. But you take how many trials you run and multiply it by the probability. Now think about why that makes sense. How many times does Max get his shoes on the correct feet if he's guessing? 5. Well, excuse me. At what rate does he get his shoes on the correct feet if he's guessing? 50%, half the time, right? So, half the time he should get his shoes on the correct feet. Half the time. So if we run 10 trials, it should be 5. It should be 5, yes? Now, do you have to know this formula? No, because if you have the distribution in your TI, what can you do? What can you do? You can run one bar stats. Always. It's a weighted average. It's a weighted average. You can run one bar stats, yes? You can run one bar stats happily. Run one bar stats, and it will give you the average. Let's do it.
5.
Oh, there you go.
That was exciting.
That was very exciting. There's your average, it's 5. Now, the one thing that is pretty slick is, it also gives you a standard deviation. Now, that is only useful when? Oh, well, but we do, which is nice. But when would you use it? When would you use this? I'm asking a question back from about 3 weeks now. It's a bastard question. What? Say that again.
Are you doing polls with
Yes, exactly. What do they do when they look at a Gallup poll? What do they do with standard deviation in a Gallup poll? What do they draw around their estimates in their polls? Their margins of error, right? They draw pluses or minuses around polls, right? Now you guys learned in this class, we did that too. Plus or minus a standard deviation, plus or minus 2 standard deviations, plus or minus 3 standard deviations, right? When was the only time we felt comfortable doing that? When you had what kind of data?
Bell curve.
When you had roughly bell-shaped data. When the data was too skewed, the standard deviation was usually too skewed too, because it chases the average, which chases the outliers. But when you have bell-shaped data, it's okay to use standard deviations to kind of get the idea across. Now, FYI, this is another FYI, it's not a necessity to memorize this. But sometimes, depending on who you take stat from later, if you take 244 or 302 or 30, whatever they teach over at OSU, there's also a formula for the standard deviation. I would file this one. Well, if you guys take later stat classes, you'll save your notes, right? I'm assuming you will.
No.
Yeah, of course.
Yeah.
Save right next to the fire pit. No. So if there is a really, really clean formula for this, it's actually beautiful. You don't have to run one of our stats to get it. The standard deviation, which we can call sigma because it's the whole population. And watch this. This is so freaking beautiful. It's root n times p, Gesundheit, times 1 minus p.
Really?
It is. So if you know, Gesundheit, those are good sneezes. If you know how many times you run the trial, N, and you know the chance of success Gesundheit on one trial, you can calculate the standard deviation by simply running these numbers together. Watch, I'll show it to you. If you do square root of 10 times a half, you get 1.581138. Does that number look familiar? It's that. Isn't that badass? You might not think so, that's okay. It's okay. It's okay. I remember learning it. I was in your guys' seats years ago, sitting in, they called it Stat 370 at the time. And the prof said, before doing the Max experiment, because Max wasn't even around then, and before doing the chicken experiment, because I don't care about chickens at University of Delaware, he just simply said, for a binomial random variable, the average is given by n times p, and standard deviation is given by n times p times 1 minus p. Now this one is pretty intuitive. You guys figured this out last week without even any prompting. This one, that's not intuitive at all. So what I did was, I was sitting roughly where Scott was, I'm like, hey, Dr. Taylor, why? What do you mean why? I was like, why does it equal that? Like, why is it that if you took the distribution, which is here, like this is the distribution, right? And the average is found by doing this times this, plus this times this, plus this times this, plus this times this, all the way down. That's the average. The standard deviation is then found by doing this minus the average squared, plus that minus the average squared, times that, but you have to do this crazy calculation. Why would it be that it would simply collapse into a formula of that neat? And he said, I don't understand your question. I'm like, I think it's a pretty simple question. What this seems like is black magic to me. It seems like this is too neat. And as a mathematician and as a statistician, when things get too neat, that's when Harrison Ford starts running away from the one-armed man. When the data's too pretty. You get what I'm saying here, friends? I'm saying that although I understand why this is so pretty, it's fairly straightforward, this doesn't seem like it should be that pretty. He never did tell me. He eventually copped out on the, well, I've been teaching this stuff for 30 years. I'm like, all I'm asking for is justification. I went home and proved it myself. 3 pages of algebra later, I got the formula to fall out. If you want to see it, and or if you're having trouble falling asleep at night sometime, log on to the enrichment page of the website and there's a proof for both the mean and the standard deviation. It's super rad. I remember doing it and being like, I got done, I'm like, ah, son of a bitch. That's awesome. Totally awesome. If you ever need the formula, I doubt you ever will, honestly. I doubt you ever will. Because the thing is, the average is useful all the time with a binomial. But this one's only useful when it's roughly symmetric binomial data. As soon as it starts sliding to the chickens, 90-10, 10-90, the standard deviation starts getting useless because it gets too skewed. But as long as you have symmetric data, the standard deviation's great. Faith, please.
So when it's like 50-50.
50-50, 60-40, 40-60, somewhere around 50-50. Yes, ma'am. Yes, ma'am. Thank you. So here's an example. Leave your TIs the way they are. Here's an example where I wouldn't use it. If I ran dist fill again, but I bought 10 chickens, but I bought them sexed. Right? I bought them sexed now. Here's what that distribution looks like.
Okay.
That's what it looks like when you buy 10 sexed chickens at 90%. Notice, the most likely outcome is 9, as it should be. 9 out of those 10 should be girls, and there should be 1 rooster. That's why the probability of all 10 being girls is a little bit less than the chance of having 1 boy and 9 girls. That should hopefully make sense. You know why? Because you guys understand this formula. Intuitively, this formula makes sense. Intuitively, that formula, when you buy a bag of Skittles, let's say the bag of Skittles contains 100 candies. How many should be blue?
How many colors?
Say it again. There's 5 colors.
What is that, 20?
20 should be blue. I thought somebody said 20 over there. 20 should be blue. How many should be red? 20. How many should be?
Yellow.
Is it yellow? I don't know what color Skittles are.
We're switching between like the smoothie flavors and the classic.
Let's just go with 5 colors. Here's a tricky question. You buy a milk chocolate bag of M&Ms.
That's a good one.
120 candies in it, because there are 6 colors. Let's make this easy. 120. How many should be red? It's not that simple, because they're not evenly distributed. We test this in Math 244. Give everybody in class a bag of M&Ms, crack them up, we count the colors, put them up on the graph, and take a look.
Because if we say it's 20, we're assuming that it's the average.
And that is not what they release them as. They don't release M&M milk chocolate the same way Skittles releases their colors. Skittles goes 20, a fifth, a fifth, a fifth, a fifth, a fifth. M&M's doesn't. They have these goofy ass percentages that they claim are from customer surveys they've done. I call it BS. If you've ever been by the office, if you ever come to my office, as you walk into my office, I have a stream of letters that I have written to the Mars company, and a stream of their letters they've written back for me. Every term, we check the colors. And every term, for 10 years, except for one, they've been off the colors they claim. And every term, I say, if you just send us more candy, I'll give you what colors you're actually doing so you can stop lying to the public. And they send me back a form letter every term. So if you take me for 244, we'll do it again. That's what I'm saying. I'm just saying, it's one of those things. But the thing is whether you're testing Skittles, chickens, or Max's Crocs, you have to know a probability to put in a test against. So we're testing against whether he's guessing or not. It's the same exact thing as Skittles at this point, except instead of 5 outcomes, there's 2 outcomes. He either got them or he didn't. Fair enough? Okay, so here we go. Now comes the analysis part. Let's put the graph back up that we had before.